Hey, this is Horner. We're going to look at section 20.1 and 20.2 for problems. And the first problem is number 1 in figure 20.2. So this is the figure. We have a metal rod. It has a length of L. So we're only worried about what's bound by these two bars. And it's moving to the right with a speed of V. They want to know what is the current in the rod in terms of VB, L, and R. So for this one, we know that the induced EMF in this is equal to the velocity times the magnetic field times the length of the rod. And so we know that current is equal to the EMF divided by the resistance in the resistor that we have here. And so that's equal to V times B times L all over R. So just very straightforward, very easy to do. For letter B, the next thing they want us to do is they want us to figure out in which direction does the current flow. So for this one, we know that the force would be equal to negative E, which is an electron, times the speed, and we cross that with the magnetic field. We see the magnetic field is going into the page, so that is your middle finger is going into the page. Your index finger is going to the right, so this is your index finger. And if you do that, you'll notice that your thumb does point up. So your thumb points up, points in this direction. So that is the direction of the current. Now, ideally, this one's a little confused. Well, let's go ahead and finish this one. It is counterclockwise then, so that is the direction of the current. Everybody says, yeah, but it's an electron. You're right. The electron, the force on the electron would be down, so the electrons would be moving to this direction. If that's true, this end becomes negative, this end becomes positive, and we know current always goes from positive to negative. So that's why this one confuses some people. We don't want the force on the electrons. We do it first because we want to know the electrons are moving clockwise, but current, remember, is always the opposite of the flow of the electrons. And we can thank Ben Franklin for messing that up. Let's go ahead and take a look at part C. It says, what is the direction of the magnetic force on the rod? And we know that the magnetic force is equal to I times L cross B. That means that our index finger is going to point up. So this is my index finger is going to point in this direction. I know my middle finger is pointing into the page. And if I do that, I notice that my thumb, well, we can actually do it on the rod here, points to the left. And so that would be the force due to the B field. So let's go ahead and take a look at the next one, which would be letter D. They want to know what is the magnitude of the magnetic force in the rod, and they want it in terms of VB, L, and R. So force is equal to ILB. We can rearrange this then. We know current is VBL over R times LB. And so now we can square the b's. So we've got VB squared times L squared all over R. All right, so that one was pretty easy. Let's go ahead and take a look at the next one. Next problem is number 4. We have the same figure here. They want to know what would be the magnitude in terms of V, L, R, and B, and the direction clockwise or counterclockwise of the current if the direction of the magnetic field, and the first one is into the page. So we've really already done this one before. We know that it is going counterclockwise because our index finger is pointing to the right. We know that our middle finger is pointing into the page. That makes our thumb point up. Okay, so that would make this counterclockwise. So we're going to say this is counterclockwise. I know the current is equal to the EMF over R, and that's going to be equal to VBL all over R because E is equal to VBL for this situation. For letter B, which is the next part, if the magnetic field was pointing to the right, so you have to ignore the x's that are here. Let's just say that the magnetic field is pointing to the right, so this B is really the lines and not the x's. What we'll do is we will take our middle finger and the middle finger will go to the right, but our index finger also goes to the right, and because they're pointing in the same direction, then there is no force at all on this. I'm sorry, there's no current that's going to run through it, so here we say that the current is equal to 0. For letter C, when we do it, it says up, and so in the plane of the page. So if we have a magnetic field that is pointing in this direction now, so it's going up like this, our middle finger would be going up. We know our index finger would be pointing to the right, and that would be the speed, so that's our index finger. And so our thumb would actually be pointing to us. So this is our thumb. Thumb would be pointing to us, and so that would be the force, and that would be the current. Now the problem is let's take this thing and let's just take it and turn it on its side so we see it. So now we're looking at it like this. And now we have the force on the rod is pointing up. So the electrons are getting pushed up, which induces a current down, but that does not make it flow clockwise or counterclockwise. So for letter C, the current is also 0 because the electrons are not flowing through the circuit, they're just getting pulled up to the top of that rod, making the bottom part of the rod positive. Let's go ahead and take a look at the last one, which is letter D. So now it has components both out of the page and to the right with a 20-degree angle between the field and the plane of the page. So if we're looking at the page from the side, this is the way the magnetic field would be, and it would be at a 20-degree angle. And because of that, we're going to say that I is equal to VB L, and so this is B perpendicular to L all over R. So this is V times B times the sine of the angle times L all over R. So this is equal to VBL over R times the sine of 20 degrees. The sine of 20 degrees is 0.342, and that would be times VBL all over R. And that would be your magnitude. So the direction would be this. You would have to take your middle finger, and it would be pointing slightly up and to the right for what we're doing. Kind of out of the page. Your index finger is pointing directly to the right, and so your thumb would be pointing down. So if we looked at this kind of from the side like we're doing here, this would be your middle finger. Your index finger is going to the right, so we don't worry about the X direction, we just want to worry about the Y direction here, and because it's 20 degrees, it's reduced in size, so that's that 0.342. So we're really looking at the B field that's going kind of like this. This would be our velocity for our index finger, so your thumb would be pointing straight towards you, and then if you rotate that back down, you'll notice that then the current is going to run in this direction, and so now we have a clockwise direction for our current as that thing moves. That was number 4. Let's go ahead and take a look at the next question, which is number 6. It says when the armature of an AC generator rotates at 15 radians per second, the amplitude of the induced EMF is 27 volts. They want to know what is the amplitude of the EMF when the armature rotates at 10 radians per second. So because it's slower, our V final should be less than 27 volts. We do know that the amplitude, so from the lecture kind of video that you saw, the notes, oops, I hate it when it does that. So the amplitude, oh, it's going to do it again. So the amplitude, here we go, oh wow. There's a dead spot on my board, I guess. Okay, so let's try this again. We know that the amplitude of E is proportional to omega. So this would be our EMF. This is our angular frequency or angular speed in radians per second. So we know that E is proportional to omega. So we can say that the final EMF over the initial EMF is equal to omega final all over omega original. Now we can say the induced EMF is equal to the angular frequency final over the angular frequency original times that original, the original EMF. Let's go and plug everything in. We have 10 for the original. We do have, I'm sorry, for the final, we have 15 for the original. And then we're going to multiply that times 27 volts. When you do that, you should end up with 18 volts. That was number 6. Let's go ahead and take a look at the next one, which is number 7. We have an armature of an AC generator. It's a circular coil. It has 50 turns, and the radius is 3 centimeters. So anytime you have centimeters, we always want to change that. That's 0.03 meters. Our equation for this one is the EMF is equal to the angular velocity or the angular frequency times the number of turns. So that's why you see the 50 turns here, times the magnetic field times the area, where area is equal to pi r squared. Our angular frequency here, well, let's go ahead and do this. We want to find out what is the magnetic field. So that puts the EMF on the top, omega NA on the bottom. This would be 17 volts for our potential. Down on the bottom, we've got to convert the omega. So we're going to take this 350 revolutions per minute, and we've got to convert it to radians per second. So we know that 1 revolution is 2 pi radians. We also know that 1 minute won't work. We're going to have to get that in seconds, so that's 60 seconds. This was 17 volts of potential on the top. Then we have to do the area, which would be, I'm sorry, we have to put in the number of turns, which is 50, times pi, times 0.03 meters, and we're going to square that for our radius. Now that we have all our numbers, if you go through and do your math, you should get somewhere close to 3.3 Tesla. Remember, that is the unit for magnetic field. For number 8, it says the armature of an AC generator is a rectangular coil, and here this one is 2 centimeters by 6 centimeters. So remember, we said that these coils can be any shape, and we just have to find the area for them. It's immersed in a uniform magnetic field of 0.45 Tesla. If the amplitude is 17, they want to know what is the angular speed of the armature when it rotates. So we're going to start with our induced EMF again as the angular frequency times the number of turns times magnetic field times the area. And so we know that the angular speed would be equal to the EMF over N times B times A. This is 17 volts again. We're going to divide that by 80. So 80 is the number of turns. Our magnetic field is 0.45 Teslas. And then we've got to have an area of 0.02 times 0.06. It's because this is in centimeters. We want to convert it. So that one's good. Now we go ahead and solve, and we should get 390 radians per second. And then if you want to, you could convert that to revolutions. All right, so for the very last one, this is number 9. I have a solid copper disc. So here's my solid copper disc of radius r. So we can go ahead and put our radius in. So here's our radius, r. Rotates with an angular velocity perpendicular to a magnetic field B. The figure shows the disk rotating clockwise and the magnetic field is into the page. Is the charge that accumulates on the edge of the disk positive or negative? So to figure that out, we're going to say that the force will be equal to negative E times V cross B. The electrons here are forced to the center of the disk due to the right-hand rule. So our force here, remember, is a centripetal force, so we're going to move it towards the center. So all of those electrons are going to move towards the center. If the electrons move towards the center, then on the outside of this disk, we should have a positive charge accumulate. on the edge of the disk. For letter B, the next thing they want us to do is they want us to find the potential difference between the center of the disk and the edge. Well, we have to think of the disk as a large number of thin wedge-shaped rods, I guess. So the center of the disk is the rod at rest, and the outer edge moves at a speed of v is equal to omega r. So that's just the tangential speed on the outside. The rod moves through the perpendicular magnetic field at an average speed of 1/2 omega r. So those are your hints. So we're going to use our same equation. The EMF is equal to V BL, where L here is going to be equal to your radius. Your change then in your EMF, which is your change of potential, is equal to your velocity. So we'll do that, times B times L. Our velocity we said was omega r over 2, or 1/2 omega r, so omega r over 2 times B times r, and so that gives us 1/2 omega B r squared. And that is your final answer. And just as an addendum to kind of help you understand why the electrons are getting forced in, I think the best thing to do is to use the right hand rule. So your index finger is actually going to move along a tangent line with the disk here, since it's going in this direction. So there's our tangent point. This would be our index finger. Our middle finger will be into the page. And if our middle finger is into the page, my other finger is doing that, then I know that the force on a proton would be going this way. But remember, we do have electrons that are getting moved to the center. So remember, we were going to do the opposite. So that's why the electrons go towards the center, and why the charge on the outside all the way around, because we could just continue to do this. Oops, there goes my pen again. We could continue to do this all the way around, and you would get the same thing. You'd still have those electrons moving towards the center. And that is the end of 20.1 and 20.2 problems.